I welcome you all in this presentation, and we have talked about the weldability of the metals strengthened by the various mechanisms like solid solution strengthening, grain refinement, precipitation hardening, dispersion hardening and transformation hardening, and the responses of the weld thermal cycles as well as the plastic deformation associated with the deformation based joining processes is different on each metal system. But any metal system which is being welded will have the effect of the various strengthening mechanisms. It is not just the single strengthening mechanism which will be offering the required combination of the mechanical properties to the metal. So, a metal basically comprises the effect of various strengthening mechanisms. So, if that is the case, then what will be the net set of the properties which will be achieved on fusion welding or on the plastic deformation based welding processes. So, let us take like simple aluminum. In aluminum we have like work hardenable metals of 5000 series aluminum alloy and precipitation hardenable metals of 2000, 6000 and 7000 series aluminum alloys. Responses to the fusion welding as well as deformation of these metal systems will be different, and that is what we have talked under the different categories. But whenever we make any alloy or metal for commercial applications, it will have the combined effect of the various mechanisms which will include like the work hardening mechanism due to the set of the manufacturing processes which are used to give the desired size and shape, like cold rolling, forging, etc., or wire drawing are being performed in the metal to give the desired size and shape. So, they will have the work hardening effect, whether it is designed for that or not, or whether the metal has been strengthened by that mechanism or not. Whenever there is work hardening or controlled thermal cycle application during the manufacturing, there will be the grain size variation. So, there may be the coarsening or there may be the refinement of the grains. For example, low cooling rate experienced during the casting will be leading to the coarse structure, while the higher cooling rate experienced during the welding in the weld metal will be leading to the fine grain structure, or in case of the thermomechanical treatment, the refinement of the grain structure is achieved. Apart from the grain refinement, like in some of the steels, strengthening is realized through the formation of the precipitates. So, it is also possible that the metal is having the effect of some of the precipitates or some of the phases which are being realized through the controlled phase transformation. So, I mean to say a metal may have the effect of the combination of the various strengthening mechanism at the same time. So, which effect will dominate in determining the final properties of the metal, that is important to talk about. Like if we take a simple metal which is a aluminum alloy of work hardening type. So, sometimes what we see, whenever material is deformed in very controlled way plastically, it is work hardened as well as it is refined, and which helps in increasing the mechanical properties and hardness of the weld zone systematically. So, if we see this one, like the weld metal subjected to the controlled plastic deformation for developing the joint. So, the zone which is experiencing the plastic deformation will be offering the higher hardness and the strength, while there may be softening in the nearby zone due to the loss of the work hardening effect due to the heat generated during the welding process. So, there may be hardening of the weld metal, and at the same time there may be softening of the heat affected zone. So, weld metal and softening of the heat affected zone. So, this is HAZ region and this is HAZ region and weld zone. On the other hand, what has been observed? So, this is the case of the work hardening effect, where both fine grain structure as well as the work hardening effect will be imparted. On the other hand, if it is the precipitation hardenable aluminum alloy which gets its strength from the formation of fine precipitates. So, a controlled plastic deformation of the weld metal near the fairing surfaces will be leading to the very fine grain structure, but the fracturing and the controlled plastic deformation followed by the high heat generation leads to the reversion and complete dissolution of the precipitates. So, here this region has no precipitates, but very fine grain structure. In this situation, if we try to just see the properties of the weld nugget area, then we will notice that despite of the refinement, there has been sharp drop in the weld metal hardness and weld metal strength. So, here there is a contradiction, like despite of the refinement we are getting the reduction in strength, because this metal was primarily designed to have the strength from the precipitates, and if these precipitates have got dissolved, so refinement and solid solution strengthening will not be contributing that much as it was designed for the precipitation hardening. So, although dissolution will be leading to the solid solution strengthening and the fracturing and refinement of the particles will be leading to the grain refinement, but despite of combination of these two strengthening mechanism, major factor which was contributing to this kind of the metal system was the formation of the precipitates, and if these precipitates have lost, then we will be losing the hardness, we will be losing the strength of the joint. So, this is the case where like solid solution strengthening and the refinement are not working at all. It was the formation of the precipitates that was primarily responsible for the strength of such kind of metal system. So, that is why it is necessary to see the relative effect of the various mechanisms, how the relative effect of the various strengthening mechanisms and how these respond to the weld thermal cycle or the controlled plastic deformation during the welding. So, just for an example, I will take initially an example of the aluminum, like when pure aluminum is used, the UTS sigma U ultimate strength, in maybe unit we can understand it is the relative value. So, strength is say 6 units and the percentage elongation is 60% or 60 units, and the alloying to strength or yield strength ratio is 1. There is no alloying and strength is minimum for this system, and if we take aluminum of commercial purity which is 99.9% pure, the strength will be somewhat higher due to the presence of these impurities, say 13 units, and the ductility will be lower, say 45 units, and the alloying or impurities to the strength ratio will be somewhat high, say 2. If we talk of the another when the aluminum alloy is strengthened through the solid solution strengthening approach by controlled alloying, there is a further increase in the strength or higher strength is realized of the 16 units as compared to the pure aluminum of 6 units, and the ductility is somewhat reduced. Whenever there is an increase in strength, there will be loss of the ductility as well as the toughness, and the alloying to the strength ratio here is 2.4. If the aluminum alloy is strengthened through the work hardening approach, work hardening alloy, then the strength is 24 unit, and the percentage elongation is 15%, and the alloying to the strength ratio is 8.8. Then dispersion hardening, like the addition of the Al2O3 or silicon carbide or TiB2 or some other alloying, some other reinforcing agents are reinforced in the aluminum matrix, then the significant higher strength can be realized of the 42 units with the reasonably good percentage elongation of the 34% and with the high concentration of the high alloying element to strength ratio 8.8. And dispersion precipitation hardening, the aluminum alloy when designed to get the strength from the formation of the precipitates, then very significant increase in the strength is realized of 83 units with the elongation percentage of the 11, and alloying to the strength ratio is 29.2. So, for unit alloying, the kind of the strength increase which is observed in precipitation hardening is maximum and then somewhat lower for others. So, if we see the effectiveness of the alloying through the precipitation hardening for increase of strength is maximum for the last approach, which is precipitation hardening alloy system, and then the effectiveness is somewhat lower for the dispersion hardening system, like this. Strength of 42 units is realized, and like say the strength increase in strength for unit alloying is of 8.8. Somewhat further lower effectiveness is observed in case of the work hardening and solid solution strengthening. So, if we see this one, effectiveness is maximum of the precipitation hardening and then dispersion hardening, then work hardening and then solid solution strengthening. So, during the welding, either by the fusion welding or by the deformation based approach, if there is a loss of the precipitates, then it will be leading to the maximum softening. Similarly, if there is a loss of the dispersed constituents, either they are due to the fracturing or their dissolution, then these will be causing the further severe loss of the hardness. Thereafter, the loss of the work hardening effect due to the recovery and annihilation will be again leading to the reduction in strength and hardness. Minimum effectiveness is there of the solid solution strengthening. So, whenever there is a loss of precipitates or the dispersoids present in the aluminum alloy and leading to the development of the either work hardening or the work hardening effect or the solid solution effect, their effectiveness is limited, and that is why we will notice either during the fusion welding or due to the deformation, loss of precipitates or loss of the dispersoids will be leading to the softening. So, despite of the refinement, despite of the solid solution strengthening, in case of the precipitation and dispersion hardening alloys, there is a loss of strength, loss of hardness. So, this is the the net effect for the aluminum alloys and the magnesium alloys which are precipitation strengthened. Now, we will see the another case where like say the transformation hardening systems like steels or ferrous systems. So, in these cases the strength is offered of course through the solid solution strengthening, grain refinement, work hardening, transformation hardening, like the kind of the phases which are being formed. Again, the effectiveness is maximum even for a given composition. If we see the effectiveness of the work hardening is a transformation hardening is maximum, then somewhat lower for the work hardening, further lower for the grain refinement and further lower for the solid solution strengthening. So, as far as increase in the strength and hardness is concerned, the maximum effectiveness of the transformation hardening systems come from the phase transformation, then work hardening, then grain refinement and then solid solution strengthening. And that is why sometimes we will notice that if the type of phase is same, which is like say the ferrite. So, if the ferrite is coarse and ferrite is fine, then of course, the fine ferrite will be leading to the better properties as compared to the coarse ferritic structure. But if the metal has been subjected to the annealing and the same has also been subjected to the work hardening, then the work hardened metal will be offering the better properties as compared to the annealing, even if there is no change in the phases. Say for example, if annealed steel is subjected to the welding through the plastic deformation approach. So, it will have the work hardening effect in the weld zone, while in other regions there will be annealing the base metal, minimum effect of the minimum hardness and the lower strength. So, if we plot the variation in the hardness for the annealed base metal, annealed steel, then it will in the weld zone it will be offering the greater hardness due to the work hardening effect as compared to that of the annealed zone. Obviously, annealed zone will have the annealed base metal have the coarse structure, while the plastically deformed or work hardened metal will have the fine grain structure as well as the work hardening effect. For the same conditions, same phase, fine grain structure will be offering the higher properties, but if despite of the fine grain structure, if the metal has been work hardened, then it will be offering the better properties. Like instead of annealing, if we take the example of normalizing, which offers the finer grain structure, but further if we go for work hardening, then work hardening during the deformation during the welding, then it will be offering us the better mechanical properties. So, which suggests that work hardening is more effective than the grain refinement. Sometimes despite of the coarser grain structures, we get the higher properties. That is the case of the phase transformations, like in a steel, like say the steel, the base metal is having very fine grain structure in form of fine perlite and the ferrite. Average grain size is say 8 micrometer. And due to the welding, like say either fusion welding or the deformation based process, heat generated leading to the coarse grain structure in the heat affected zone. So, this coarse grain structure may be leading to the very coarse grains in the heat affected zone and say like 30 to 40 micrometer. But since the phases being formed are like say the phases are different, now we may have the benite martensite or perlite martensite mixture. Despite of having the coarser grain structure, since these phases are harder than the simple ferritic and perlitic structures, that is why we will be getting the greater hardness and greater strength in the heat affected zone. So, the grain size and work hardening is not that effective as the kind of phase transformation, because the phases being formed will be able to regulate the mechanical properties in bigger way as compared to that of the simple solid solution strengthening or the grain refinement or the work hardening. So, work hardening will also be not effective if there is no phase transformation in such kind of the metal systems. Now, we will see the what kind of the basically in the weldability of the metals, we have to talk at length about the weldability of the ferrous systems. So, which primarily comprises the weldability of steels. So, the steels during the welding primarily suffer from the loss of toughness of the weld as well as heat affected zone. This is called embrittlement. So, their ability to sustain the impact loads is reduced drastically. Another one, lot of heterogeneity in mechanical properties is observed, which can be there in both form, like softening as well as hardening. Mostly it is hardening which is observed, but in some of the categories even softening is observed. I will give examples of both. Like in most of the steels, we will see the weld zone as well as heat affected zone experiences the martensitic transformation, and therefore both these zones offer the higher hardness as compared to the base metal. That is why failure mostly occurs from the base metal, not from the HZ and the weld zone. But if the steel is in the QNT conditions, then we will notice that due to the higher cooling rate during the welding, the weld zone invariably experiences the martensitic transformation, and so the higher hardness, but the zone next to the weld metal is over tempered, and that is why this zone experiences the loss of hardness. So, the base metal is having higher hardness, but as we approach to the heat affected zone, hardness is reduced. Then in the weld metal again hardness is increased, then hardness is reduced. So, the reduction in hardness adjacent to the weld metal and away from the this adjacent to the weld metal, which is the heat affected zone, this loss of hardness or which we can say this softening is basically attributed to the over tempering of the steel. So, this kind of over tempering is more severe if the steel is welded by the SAW or SMAW processes, and even in the high this is also observed in case of the laser welding and electron beam welding process, where energy density is very high and limited heat is used for the fusion of the metal. So, apart from these two factors governing the weldability, like the cracking tendency in form of solidification cracking, cold cracking or hydrogen induced cracking, and underbead cracking, reheat cracking. These are the common crackings which are observed in the steel under the different conditions, and so these also affect or determine the ease of welding of steel significantly. And the low carbon steels, low alloy, low carbon steels having the higher melting point, they also show the tendency of the porosity development and inclusions in case of the rolled steels. So, now we will go through the different category of the steels which are commercially used, and from the welding point of view how these are categorized. So, the steel categorization, steels, basically these are carbon steel categorization from the welding point of view. So, there this categorization is based on the composition, mechanical properties, heat treatment, ability to withstand at a high temperature. So, high temperature resistance and corrosion resistance. These are 6 categories: corrosion resistance or corrosion protection. So, the grouping of the steels from the welding point of view is about the carbon or low alloy steels. This grouping is primarily based on the alloy the composition of steel. Carbon steels primarily comprise the carbon up to 1%, with the manganese 1.65% and silicon 0.6%, while the sulfur and phosphorus concentration is maintained below 0.05 level. Higher concentration leads to the increased tendency for the solidification, cracking. So, the steels based on this like the low carbon steel or the medium carbon steel or high carbon steels. So, low carbon steels like those having less than 0.25% carbon, medium carbon steel like 0.25 to 0.5% carbon, and those having the carbon greater than 0.5% will be falling under the high carbon steel category. And most of these steels are used in as rolled conditions, annealed or normalized condition. Since the heat treatment condition of the steel significantly governs the weldability, that is why it is important to know about the condition of the steel or heat treatment condition of the steel. Another grouping is based on the minimum yield strength or the mechanical property, which is called HSLA, high strength low alloy steels. High strength low alloy steels, these are designed to have the strength from about 280 to 480 MPa. That is the minimum yield. This is the yield strength range for which these are designed by the controlled addition of the alloying elements, and these are mostly used in form of the in the as rolled condition, normalized condition uh, for the welding purpose. Then third grouping is based on the heat treatment aspects. So, there are two categories of the steels in this group. One is the quenched and tempered steel. These steels are obviously these are quenched followed by tempering, so that a higher strength range can be realized in this category, and they are designed to have the yield strength from 350 to about 1040 MPa, and mostly these are welded in the heat treated condition, QNT conditions, and PWHT mostly is not required for these steels, and if at all some kind of the PWHT is needed, then that is primarily done for the stress relieving treatment. And therefore, since the PWHT mostly are not required for this purpose, and therefore, these are mostly used for the construction purposes, where heavy structures are to be designed to be made, then QNT steels are used, because subsequently these do not require extensive PWHT for enhancement of the mechanical properties, but these sometimes the stress relieving is needed in order to avoid, in order to reduce the residual stresses. Then there is heat treatable steels. Heat treatable steels. Heat treatable steels, they have the higher carbon content than the HSLA and the QNT steels, and higher alloying concentration, alloying elements. So, these respond very good to the heat treatment. Of course, they offer high strength and high hardness, but of course, this will be happening at the cost of reduction in the percentage elongation and the reduction in the toughness. These steels are mostly subjected to the post weld heat treatment after the welding in order to restore the properties after after the welding, because because these respond very rapidly to the weld thermal cycle after the welding. So, these will be leading to the embrittlement of the weld as well as the heat affected zone. So, in order to restore the toughness as well as other mechanical properties, the post weld heat treatment is given to these steels. Next category of the steel is the heat resistant steels. These are basically chromium molybdenum steels. There are various chromium molybdenum like 1 chromium, 0.5 molybdenum, 2.25 chromium, 1 molybdenum, then 9 chromium, 1 molybdenum. So, there are various combinations of the chromium molybdenum steels which are used for the high temperature applications like 600 to 650 degree centigrade in thermal power plants. So, these need to be welded mostly in the annealed condition, normalized condition, or in the QNT conditions, and these after the welding, mostly before putting such kind of the weld joints of the chromium molybdenum steels, the PWHT is given in order to have the expected performance during the service of these steels. Mostly these then there is one more category, that is the steels offering the good corrosion protection, like these are the galvanized steels, or these are like pre-coated steels, coated with the zinc, aluminum, primarily for the improved ambient corrosion resistance, and this can be performed, means coating of these metals can be performed through the thermal spraying or hot dipping method. When such kind of the steels are welded, of course, the zinc and aluminum can interfere during the welding, and that can in turn govern the weldability of the metal. Now, I will summarize this presentation. In this presentation, basically I have talked about that how the weldability of the metals which are having the effect of the various strengthening mechanisms is affected, and what are the various categories of the steels which are grouped on the basis of the welding. So, there are 6 categories of the steels, and this categorization of such kind of the steel is based on the composition, mechanical properties, heat treatment, the corrosion resistance, and the heat resistant applications. Thank you for your attention.